So the title of this presentation is Modeling, Verifying and Testing the Contract Automata Runtime Environment with UPPAAL. This paper has been presented at Coordination 2024. I am Davide Basile of the Formal Methods and Tools Lab of ISTCNR Pisa. This work has been done in the context of a European project called Adventure. So these are the banner of the acknowledgements to the project. I'll start with the overview of the presentation. Firstly, I will discuss the background of the Contract Automata Runtime Environment and UPPAAL. In a nutshell, in this paper, we modeled this distributed application that is called Contract Automata Runtime Environment with UPPAAL, and through the model we generated tests and we performed model checking. In this paper, in this presentation, I will discuss the formal model, that is the abstractions that have been made to model the application, and the adequacy, that is how the model has been related to the source code. Then I will discuss the formal analysis, focusing on the tuning of the parameters of the model and the statistical and exhaustive model checking, and I will conclude the presentation. This is not a work about contract automata. However, it may be helpful to provide some insight on what this formalism is, since we are modeling its runtime environment. Contract automata are a special type of finite state automata that were enhanced with a partitioned alphabet of actions, of offers and requests, plus a special idle action. This formalism has been introduced 10 years ago to model debits and credits in behavioral contracts using an automata-based formalism. It has since then evolved towards a model-driven engineering technique to develop service-based applications. An automaton has a rank. The rank represents the number of services inside the automaton. For example, here we have an automaton of rank 3, meaning that there are 3 services inside this automaton. We see that the states and labels of transitions are a list of elements. The size of this list is the rank of the automaton. Furthermore, labels are a list of basic actions that are constrained to be one of these 3 types. Either there is an offers and all the other are idles, all the other services are idle, or there is a request and all the other services are idle, or 2 services are matching the corresponding requests and offers while all the others are idle. The methodology of contract automata is that we can start from contracts of rank 1, for example the server and the clients. We compose them with this operator of composition to obtain a spurious composition. A spurious composition is a composition where we have unwanted behavior. For example, one property that we are interested in enforcing in this framework is the agreement between the parties. This means that each request of each service is matched by a corresponding offer. To do that, we perform an automatic refinement of the composition automaton to obtain this so-called orchestration automaton. This is basically done by readapting the most permissive controller synthesis from supervisory control theory to obtain an orchestration of contract automata. This is an orchestration automaton where we see that all requests are matched by corresponding offer. An important aspect is that contract automata completely abstract away from the underlying mechanism that is used to realize the orchestration. We only see the orchestration automaton. To concretize this aspect, later, last year in 2023, at Formal Methods, the Contract Automata Runtime Environment has been introduced. This is a middleware application realized in Java that basically is used to realize service-based applications that have been specified by means of contract automata. This software is open source and publicly available here, and in this source in this folder there is also the information and the model that has been presented in this paper, the UPPAAL formal model of the application. This also represents part of the documentation of the software. The two main classes are the runnable orchestrator and the runnable orchestrated contract. As we see in this diagram, the runnable orchestrator is basically an implementation of an orchestrator that reads the orchestration automaton and communicates with the services. Each service is represented by a runnable orchestrated contract. This is a wrapper that is responsible of pairing the specification given as a contract automaton of rank 1 with the service implementation. Here the idea is that a service implementation is basically a class whose methods are in one-to-one correspondence with the actions of the contract. During the orchestration, the runnable orchestrated contract receives commands from the orchestrator, and in case the corresponding action is allowed by the contract, the corresponding method is invoked. Otherwise, a contract automata exception, a contract runtime exception is raised. More information on this can be found in this paper. Two main aspects to implement, to specify when instantiating the classes of the contract automata runtime environment are the realization of actions and choices. Currently, there are two possible implementation of the actions and of the choice that are currently made available by the framework of CARE. For example, concerning the choice, this means that when the orchestrator has to perform a non-deterministic choice, it can do this in two ways. In the dictatorial implementation, the orchestrator decides on its own. In the majoritarian choice, basically the orchestrator interacts with the services to decide which branch to execute. Concerning the realization of action, this is related to the execution of a match action, of a match label of a transition by the orchestrator. In the centralized implementation, the orchestrator acts as a broker and makes the two services interact with each other by means of the orchestrator. Instead, in the distributed implementation, we have that the two services directly interact with each other once the orchestrator has made them aware of their presence. Continuing, we now give a little background on UPPAAL. It is the toolbox that has been used to formally model and verify the contract automata runtime environment. It is a toolbox for the verification of real-time systems whose formalism is a dialect of stochastic price-timed automata, where we have probabilistic choices and probability distributions for delays. Automata may interact by means of channels and shared variables. In this work, we only use broadcast channels since these are the one allowed by statistical model checking. We have the possibility of performing exhaustive model checking of a dialect of CTL properties and also statistical model checking. Statistical model checking is useful when we have to scale to systems automata with a large number of states. Here the idea is that instead of exhaustively visiting the state space, we statistically estimate the probability of a formula to hold by running a sufficient number of simulations that are based on two parameters, precision and confidence. This means that the number of simulations is completely independent from the size of the state space. However, even if all the simulations, for example, are not satisfying a formula, we cannot say that the probability of this formula to be satisfied is 0, but it is always an interval that we say 0 to 0 plus epsilon with a specific confidence. So in the paper, this was one of the questions that was made during the conference. When in the paper it is said that the probability is near 0, it means that it is in the interval 0, 0 plus epsilon. This means that all the simulations that have been performed have been violating the property. Furthermore, other aspects that we have in UPPAAL are the templates. For example, these are 3 templates. The idea is that the automata may take parameters and we can instantiate them in different instances with different values of parameters. And then we have facilities for test generation, simulation, etc. This is the formal model of the contract automata runtime environment. In UPPAAL, we have global declarations, for example, the number of services and other parameters. The configuration of choice and action of care, it is here declared globally. In this version of the model, this configuration is always shared between all instances of orchestrator and services. We have only one instance of the orchestrator. We see it takes no parameters, while the services are represented by these two templates, runnable orchestrated contract and socket timeout. We see that those templates take these parameters and are replicated as many times as we want, we have declared in the global declarations. This is another version of the model that we will see at the end of this presentation, where also the configuration of choice and action is made a parameter of the template. In this case, we can have a system where the services and the orchestrator have mismatching configurations. We see that these now are parameters. It's important here to note that the runnable orchestration is basically the automaton modeling the class runnable orchestration of the contract automata runtime environment, and similarly for the class runnable orchestrated contract. We also needed this further automaton for each service called socket timeout to model the real-time behavior, as we will discuss now. In the real application, in care, the services and the orchestrator are interacting using Java TCP IP sockets. These are asynchronous with FIFO buffers, and they are blocking. What does this mean? This means that whenever a buffer of one of the applications is filled, if another service wants to send a further message, it has to wait for some position in the buffer to be freed. These socket timeouts have been modeled, these sockets of the application have been modeled by arrays in the model. It is important to understand that in the model of UPPAAL, everything is local, there is no network involved. This is just a model of the actual buffers of the real application. We have one array used for the orchestrator to communicate with the services, and one other array for the services to communicate with the orchestrator. These are replicated for the number of services, and there was a size that is specified in the global declarations. The signals that are exchanged by the services and orchestrator are abstracted away with this constant, so we abstract away from the actual payload. For example, the constant request is a signal of a request, but we abstract away from the actual request and its payload that is exchanged in the real application. We have for the templates of the runnable orchestrated contract and the runnable orchestrator these functions that are used for enqueuing messages and dequeuing messages. The only difference is that from the side of the orchestrator, it also has to specify the specific ID of the service it wants to interact with. For the rest, this is a simple FIFO queue that is implemented with this methods of enqueuing and dequeuing. Now, this is an example of two transitions for sending and receiving messages. When we have to send a message to write in a queue, we see that there is a guard, that is this guard here in green. This is a procedure that is a function that is used to check whether there is enough space in the buffer of the receiver to send the message. And conversely, whenever we want to read a message, we need to check whether the buffer is empty. The buffer is non-empty, the buffer of the recipient to which we want to read the message. In UPPAAL, locations can be also urgent and committed. Basically, these are locations whose outgoing transitions have a higher priority than the others in the network. In the paper, it is described how if we would have modeled these interactions by using these urgent and committed locations, we would have encountered deadlocks in the formal model. This was checked using model checking. More details on this are in the paper. So in this application, we modeled the operations of sending and receiving messages with unbounded delays that are whose delays are distributed and with an exponential distribution as usual, and we have the rates for writing and reading. However, this causes a scenario, there exists a trace in which even if one of these transitions is enabled, it is never executed, and the corresponding automaton waits infinitely in the source location without never executing an action. This is a scenario that invalidates the model checking of formulas that are instead satisfied in the application, because in the application we never have an unbounded delay. Indeed, in the sockets of Java, we have a timeout mechanism that is, if no message is sent between the parties within a specific time interval, then a timeout exception is raised. So we had to model this also in the formal model of UPPAAL. To do that, each service has a specific automaton that is called socket timeout. We see that this C is a clock. The idea is that we have a clock that is incremented until it reaches the timeout threshold and emits a failure message. This clock is reset whenever an operation is executed in the socket. We see that whenever an operation is executed, this is the channel synchronization. This reset signal is transmitted, is exchanged between the automaton who is performing the action and the socket timeout automaton in a way to reset the application, to reset the clock. Furthermore, from each location of the model, there is an outgoing transition to a timeout special location whenever a fail or signal is received. These transitions are not further showed in the incoming slides for readability, but they are there for each location of each automaton. So we already said some abstractions, how we modeled the TCP/IP sockets and how we abstract away from the actual payload of the communications. Another important aspect is that we abstract away from the actual contract automata application that is being implemented in care. It somehow it is like we want to verify an interpreter independently from the specific program that the interpreter is executing. In this case, the program is the orchestration. So what we have is that during execution of an orchestration, a fixed number of possibilities actually happen. Either the orchestrator is executing an action, is executing a choice between action, or is decides to terminate wherever it is in a final location. Furthermore, when it is executing a transition, the possible label is either a match or an offer, since request labels are not allowed in orchestrations. All these conditionals are abstracted away by probabilistic choices in the UPPAAL automata. By tuning the probability of performing these choices, we can model different orchestrations. We now discuss the information about traceability. So, the adequacy of the model means how we related the formal model to the real implementation. In this case, each transition is traced back to the specific line of the source code that it is modeling and a specific class. For example, from the first location, the initial location, the first outgoing transition is reading a message from the queue. This is the actual implementation of the runnable orchestrated contract. We see that when the thread is executing, the first action that is performed is to receive this message from the orchestrator, and this is exactly modeled with this transition. And we see that there is a correspondence with the line of codes. All these versions of the model are available in the repository that I showed previously, and whose link is also available in the paper. We also performed model-based testing to validate the adequacy of the model. Basically, we have that each transition that involves enqueuing or dequeuing messages produces test code for writing or reading from the specific socket, respectively. The test code is not shown in the diagram, but we can see here with this specific tab in UPPAAL. For example, here we are dequeuing a message, and the corresponding test code is to read from the socket. What happens during model-based testing is that several simulations are executed, and whenever a transition is fired, the corresponding test code is appended to a text file that is the abstract test case being generated. So, for example, here we have performed this test generation, and by clicking on Save Test Cases, we see that the specific test case are saved, and these are the instructions that are appended when executing the various transitions. Before going on, we say that in UPPAAL there are several ways, several methods of several options for generating test cases. We used the generation of test cases from queries in SCTL. These queries have been used to encode specific simulations that are relevant for the specific orchestration that deploys in the test. So for doing that, we needed to encode using further variables and these queries to encode the specific execution that we want to see in our model. And we see that in the comments we have specified the specific execution trace that we are executing and the concrete test file to which it is related. The idea is that we needed to have several models for testing all the components of the runnable orchestrator. Indeed, for example, the model testing org.xml is used for testing the runnable orchestration. In this case, the services are mimicked by the tester, so we only need to have the real runnable orchestrator class, but the services are abstracted away by these test instructions generated by the model testing org model. So in this case, it is only the model of the services that is generating the test code, while the model of the orchestrator is not generating test code because we are using this test to test the real orchestrator. This is on the converse. In case we want to test the services, we need a test code for the orchestrator. Then we have the cases of the distributed matches, because in this case a service being tested is interacting with the other services and with the orchestrator. So this was a more complicated, tricky test to make, because both the orchestrator and the other services had to have test code to test the specific service. So from these models we have generated these concrete tests in JUnit. Of course, when concretizing the test, we also needed to include the specific classes implementing the services and the specific contracts and the orchestrations. So for example, this is an abstract test and this is the concretized test. We see, for example, that in the generated test code we needed to include here placeholders like expected action that we needed then to fill with the real expected action that we have in the concrete test. And this is more or less a summary of the steps that has been made to test the UPPAAL application, the Contract Automata Runtime environment. And of course this required a lot of manual work to concretize the test from the abstract test. So concerning the information about the testing, we generated tests that cover all the transitions of the models and all the interactions between the orchestrator and the services. The code coverage, this is the window of IntelliJ, indicated that the tests derived from the model cover a significant portion of the source code, and this means that the model is not excessively abstract compared to the actual implementation. These were further corroborated by, as we discuss later, by errors that have been found in the real application during the modeling phase. So in this window, we see in this slide, we see the model of the runnable orchestrator. I will not give details of this, you can find them in the paper. There is from the initial location, there is a first phase that is used to check that the configurations of the orchestrator and the services are all the same. Of course, this is the case in the version of the model in which all services and orchestrator share the same configuration. But as I was said in the introduction, there is also a version where the configurations are not the same, and in this case there is the possibility of reaching an error location, as we verified and we discussed later. We see that these are the probabilistic choices. We can either perform a choice, decide to stop, or decide to perform an action. When we decide to perform an action, the action can be either an offer or a match. We see here encoded the various options of distributed action, centralized action, dictatorial choice, and majoritarian choice. I will not go further into the details of this model. We now move to the analysis. So the first phase was a validation through modeling. Indeed, when modeling the real application, a thorough review of the source code is made, and it is already helpful to find errors in the source code. An undetected issue was identified during the modeling that was related to the majoritarian choice. Basically, in a majoritarian choice, there is a set of services that are involved in the choice, and the other receive a skip message. In the real application, the services that are skipped will not reply to the orchestrator, while instead in the implementation the orchestrator was waiting for a message also from the services not involved in the choice. This was detected in the model because the tests that were used, in all choices all services were involved. So basically this is the loop where the orchestrator is receiving messages only from the services that have been involved in the choice. So this, when modeling this loop, this error in the source code was detected. We now move to the model checking phase. We see that there are several parameters in the model related to the delays in reading and writing, timeout, buffer size, and probability weights. We model several scenarios in the verification. The goals of this scenario was to have the realistic modeling, that is a low probability of filling the buffer, experiencing timeout, and having excessive delays. We want to have a low probability of this. but we wanted to improve the verification performances, so to reduce the state space as much as possible for the exhaustive verification. So for example, for the probability weights, these weights of choice, action, and termination have been fine-tuned to model specific orchestrations or set of orchestrations that are showed in the paper. This is the buffer size. We employed statistical model checking to derive ideal values for this buffer size. Initially, we set the buffer size to 10, and we estimated, using a specific time-bound number of simulation, the average maximum value of the size of these arrays in the network. We realized that in average, the maximum positions of the buffers that are filled are around 4, 5. So we can safely reduce the buffer size to 5. To further validate this, we performed statistical model checking by measuring the probability that one of the buffers is full by setting the buffer size to 5. And we found this probability to be near 0. Again, all the simulations that have been made were not satisfying this property, that is, the buffer was never filled. So in this case, the buffer size was set to 5. It is important to understand that these queries are not made to set these values in the real application. For example, concerning the default size of Java TCP/IP sockets, this is 8 kilobytes and it is fixed in the application. It's not a value that we want to change. It is for us unuseful to have these big size of the buffers in our abstraction of the buffers of the real Java TCP/IP sockets. Okay, so this is just used for us to have efficient verification, exhaustive verification, by reducing the size of the buffers while keeping the a realistic verification. That is, the probability of filling the buffers must be low. The similar scenario is concerning the values of rates, of delays in reading and writing, and the timeout. We want to have a low probability of timeout, high probability of terminating with a given time frame that we fixed also as a parameter, and a lower timeout threshold. This is to reduce the state space. Again, statistical model checking was employed to measure the probability of having a timeout and the probability of terminating. We tried several configurations of number of services and buffer size. For example, already with 5 services and size of the buffer set to 4, the verification with exhaustive model checking was inconclusive. In this case, we either rely completely into statistical model checking or we needed to use more powerful machines. This is the exhaustive model checking phase. Again, before explaining this, concerning the termination, since these are all probabilistic choice, the only constraint that we have when we start an execution is that in case the choice is selected, at the next iteration either an action is performed or the orchestration stop. So we never have two choices executed in sequence. However, there exists a scenario in which the orchestrator alternates choices and actions without never selecting the termination. So to check the probability of terminating, we have to check that in case the orchestrator decides to terminate, it has reached the stop location, then eventually it reaches the terminated location, the orchestrator, and also the services. And this is exactly expressed with this query. This is a shortcut for this STL property in UPPAAL. Whenever the orchestrator decides to terminate, either the orchestrator and the services terminates or a socket timeout is reached. Similarly, we have a query for the absence of deadlock. We verify that in all execution, in all possible states, either there is no deadlock, or some services experience a timeout, or there is a termination of the services and the orchestrator. And these properties are both satisfied in the model. This also is used to verify that the error location is never reached. This is because in this version of the model, the configurations of choice and actions are shared between the orchestrator and the services. When formally verifying this property in an earlier version of the model, we encountered the error that I was talking previously in the modeling of TCP/IP socket. Initially, we had urgent transitions for sending and receiving messages, and this was causing a deadlock. that was detected with the formal verification on this property, and this leads to modeling the delays in the sockets with exponential delays, and having the socket timeout included in the model. And of course, in all the queries, we also needed to check whether a timeout has been experienced. There is also the formal verification for the absence of orphan messages. This means that whenever the orchestration is terminated, all messages in the buffers have been read. This is modeled with this predicate all empty. This is verified both with the exhaustive model checking but also with statistical model checkings. Again, all properties are verified. We also have the verification of other side properties. For example, this is a property checking that there is never an execution where in all states the buffers of the services and the orchestrator are empty. This property is satisfied. We only had to rule out the execution in which the orchestrator experience a timeout before any messages has been exchanged between the orchestrator and the service. This was the only, let's say, dummy execution of the model that is ruled out with this conjunction here. Further on, there is no interference in matches property. This is a property of statistical model checking. So maybe I will just say here that in the model of the services, the runnable orchestrated contract is an automaton that is not shown in the slides. We have that at maximum, when executing a match, we have only two services that are executing this match, and all the others must not be executing a match. This is basically stating a probability that more than two services are involved in a match. And again, this is statistically model checked, and the probability of this formula is found to be 0, basically, in all the simulations that we have executed. Finally, concluding, as I was stating at the beginning of this presentation, there is also a formal verification of scenarios in which we have mismatching configurations. For this, we needed to have a different version of the model. For example, in this scenario, we have that Carl has a mismatching configuration. It has a dictatorial choice, while all the others have a majoritarian choice. We checked that there exists in all execution at some point one of the error states locations is reached or a timeout is experienced. This is also can be verified by checking that in all orchestrations the orchestrator never reaches the location start, that is, never reaches this location here, because an error is emitted at some point when communicating with the services to check their configuration of action and choice. Okay, so this concludes the presentation. I have described the modeling, verification and testing with UPPAAL of a distributed middleware that is called CARE, Contract Automata Runtime Environment. I've discussed the model-based testing and traceability for validating the adequacy of the model with respect to the source code. We discussed how statistical model checking has been used for fine-tuning parameters and the exhaustive model checking that have been made of properties of interest, safety properties. As future works, when discussing, for example, the traceability information, let me go here, we have that these lines of code are fixed to a specific version of the source code. Every time we perform a change in the source code, we need to manually update all this information. So for currently this is fixed to a specific version of the source code. It would be nice to have an automatic way to align this information in various versions. So, sorry. Let me go. And furthermore, I discussed how we performed different experiments with varying configurations to find the optimal values for our parameter tuning. These were done manually. It would be nice to have a way to automatically manage the various configurations of the experiment performed in UPPAAL. For example, UPEX is a tool that has been introduced. It is built on top of UPPAAL just for this purpose, for managing different configurations. And this concludes the presentation. Thanks for your attention.